This video is on multiplying and dividing radical expressions. In order to multiply or divide radical expressions, the radicands may be different, but their indexes must be the same. So the terms in the expression square root of 5 times the cube root of 2 have different indexes, so this expression is in simplest form and cannot be combined any further. To multiply radical expressions with the same indexes, multiply their radicands. So the nth root of a times the nth root of b is equal to the nth root of a times b. Let's take a look at some examples. Whoops. Okay. First one is the cube root of 6 times the fifth root of 6. These can't be combined because the indexes are different. This is a cube root, this is a fifth root, and even though their radicands are the same, their indexes have to be the same. So we would say that this is already simplified. Okay. Example number 2 is the square root of 45, x to the fifth, times the square root of 35, x, y to the fourth. I think I'm going to break this up a little bit. I'm going to think of this as the square root of 45 times the square root of 35 times the square root of, I have an x to the fifth times an x to the 1 gives me an x to the sixth and a y to the fourth. Okay, so the square root of 45 and the square root of 35, I could multiply those and then find some factors, but I think I'm going to go ahead and factor this a little bit. So this is equal to the square root of 9 times the square root of 5, and the square root of 35 is equal to the square root of 5 times the square root of 7. So I know that the square root of 9 is going to give me a 3. I know that square root of 5 times square root of 5 gives me a 5, and square root of 7 has to stay that way. I don't have any other 7 to pair that up with. The square root of x to the sixth is going to be x to the third, and the square root of y to the fourth is going to be y squared. So that's going to give me a final answer of 3 times 5, which is 15, x to the third, y squared, times the square root of 7. To divide radical expressions that have the same index, divide their radicands. So the nth root of a divided by the nth root of b is the same as the nth root of whatever a divided by b is, as long as b is not equal to 0. However, a simplified radical expression cannot have a radical in the denominator of a fraction. To eliminate the radical, we need to do what's called rationalize the denominator. We need to write the denominator as a rational number. We want to multiply the entire fraction by an expression that's equal to 1, so it won't change the value of the expression, and that expression needs to make the denominator a rational expression. In other words, something that does not contain a radical sign. Let's take a look at a couple examples. First one may be similar to, you may remember this from Algebra 1. So the square root of 2x divided by 3y. Can't do any dividing inside there. So I'm going to rewrite this as the square root of 2x divided by the square root of 3y. And I can't have a square root of 3y in the denominator, so I'm going to multiply numerator and denominator by the square root of 3y. And now when I multiply across the top, I'm going to have the square root of 6xy, and then the square root of 3y times the square root of 3y is just 3y. So that's what's called rationalizing your denominator. I've taken this radical expression and turned it into a rational number, 3y. And one more thing is I cannot cancel the 6 and the 3. I cannot cancel the y's because the 6xy is part of a radicand. It's underneath the radical sign, and this 3y is not under a radical sign, so I can't do any canceling there. Number 2 here involves cubed roots and is a little bit more complicated. So we have the cube root of 5x divided by the cube root of 2x squared. Now, I can't just multiply as I did up above by the cube root of 2x squared, because what I want to get towards is I want to have a cube root of 2 cubed x cubed in my denominator. Why do I want that? Because the cube root of 2 cubed is 2, the cube root of x cubed is x, and that's going to give me an acceptable denominator. So that's what I want to eventually have. So I want to ask myself, what do I need to multiply? Let's not worry about the numerator now. What do I need to multiply the cube root of 2x squared by to get the cube root of 2 cubed x cubed? So I need the cube root of, and this is like 2 to the 1. So I'm going to need to multiply it by a 2 squared in order, so that's going to give me my 2 to the third power. And then x squared, I'm going to have to multiply that by an x to the 1 to give me my x cubed on the bottom. And if I do that on the bottom, I have to do that on the top as well. Okay. So notice that now when I multiply these two denominators, I'm going to have the cube root of 2 to the 1 times 2 to the 2 is 2 to the third power. X to the 2 times x to the 1 is x to the third. I'm not going to worry about the numerator right now. I'll come back to that. And notice that that's going to give me the cube root of 2 cubed is 2. The cube root of x cubed is x. And that's the denominator I want. It has no radical in it. So now let's go ahead and deal with the top. So that's going to give me the cube root of 5x times 4x, or the cube root of 20x squared. And that's my final answer. And again, I cannot do any canceling like with the 20 and the 2 because the 20 is part of the radicand and the 2 is not. And I can't do any canceling with the x's for the same reason. To multiply two radical expressions that are in binomial form, we want to use the distributive property. And you may remember this from Algebra 1 as well. So here we have the quantity 1 plus 2 square root of 7 times the quantity 4 minus 3 times the square root of 7. Distributive property, you may remember the acronym FOIL, something like that. So 1 times 4 is 4. 1 times negative 3 square root of 7 is negative 3 square root of 7. 2 square root of 7 times 4 is 8 square root of 7. And 2 square root of 7 times negative 3 square root of 7, I want to multiply, so I'm multiplying this term by this term. I want to multiply the numbers out front, and then multiply the square roots. Square root of 7 times square root of 7 gives me a 7, or that's going to give me 42. And now I can combine, so 4 minus 42 gives me a negative 38. Negative square root of 7 plus 8 square root of 7 gives me 5 square root of 7. Okay. And my second example is 5 plus 3 square root of 2 times 5 minus 3 square root of 2. This may look familiar to you, but let's do the same method. So 5 times 5 gives me 25. 5 times negative 3 square root of 2, negative 15 square root of 2. And now distributing 3 square root of 2 times 5 gives me a positive 15 square root of 2. And then 3 square root of 2 times a negative 3 square root of 2 gives me a negative 9 times 2. So what you'll notice here is that a negative 15 square root of 2 and a positive 15 square root of 2 cancel each other out, or actually make a 0. So I have, 25 minus 18 for a final answer of 7. And you may recall that these are called conjugates of each other. In other words, it's the same terms, but one has a plus in the middle and the other has a minus in the middle. And you'll notice also that this is useful, we'll see that in just a minute, for getting rid of the square roots. And here's that example I was just talking about. If a radical expression in binomial form is in the denominator of a fraction, you can rationalize the denominator by multiplying the entire expression by the conjugate of the denominator. So here we have 11 divided by 6 plus the square root of 3. So if I multiply this by 6 minus square root of 3 over 6 minus square root of 3, that's the conjugate of the denominator, 6 plus the square root of 3, and it will get rid of the square root. So here I have 11 times 6 minus the square root of 3 over, multiplying on the bottom is going to give me 36 minus 6 square root of 3 plus 6 square root of 3, and then square root of 3 times the negative square root of 3 gives me a minus 3. So 11 times 6 minus the square root of 3. You could distribute that, but I kind of know what's coming up here. Equals 36 minus 3, 33. And I can do some canceling with the numbers out front here. So that's going to leave me with 6 minus the square root of 3 over 3. And I cannot cancel this 6 and this 3 because I'd have to have a number here in front of the square root of 3 in order to do that. So that is simplified. So in this video we took a look at multiplying and dividing radical expressions. We said that in order to multiply two radical expressions, their radicands don't have to be the same, but their indexes do. And then when we're dividing radical expressions, we want to make sure that we have a rational expression, that is, no radicals in the denominator. And we took a look at several methods of rationalizing a denominator.